Okay, so now we discussed how to approximate a function in finite element. Just like we approximate, we store the function values in finite difference and function average in finite volume. That doesn't exactly tell us how to solve differential equations, right? Also, the type of approximation we are having doesn't tell us exactly how to solve differential equations in finite element. But it turns out we don't need to do much more in finite element to be able to solve equations. Instead of projecting the function into the space, we can also project an equation onto this space. So for example, if we have Poisson's equation, a Poisson's equation is partial square u partial x squared plus f equal to 0, right? That's the simplest equation we can solve. And we can project this equation onto the space. So what do I mean by that? What I mean is I want to find a solution U. So find a solution U, let me just call UH, that is within that finite dimensional space. Okay, so that instead of having the U to be as close to a particular function as possible, we want to so that this whole thing is as close to 0 as possible. All right. Yes, do you have a question? I'm using the same F. I'm not changing the problem at all. Okay. So yeah, I'm using the same F. So this thing as close to 0 as possible. Now, if you think very quickly, you may have a question here. Okay, UH is a piecewise linear function that has a kink at each boundary, which means the second derivative does not exist, or are delta functions. There are delta functions at the grid points. So what do I mean by as close to 0 as possible? All right, you said F is, you asked the question, should I keep F as original? Yes, I keep F as original. But now that means this thing is going to be a bunch of delta functions plus an arbitrary function. What do I mean by that being as close to 0 as possible? So in order for me to explain that, let me just write it down. Okay. So just write down a slightly different meaning, a slightly different formulation of the concept projection. Okay, so let's go back to our projection. Oops, what did I do? Okay, let's go back to our concept of projection. So we have a projection that is we want to minimize over G within XH the integration of G minus F square dx. So that's our projection of F onto the space XH, right? So we are solving a quadratic minimization problem, which means if this is solved by the function fh, that means any perturbation on this fh cannot improve this distance or this norm of distance. Then it means that this thing is minimum. Fh minus f squared dx is going to be less or equal to this plus any delta as a function of delta f, I mean actually delta g, right, minus f squared dx. So for any delta g, for any perturbation from that optimal, you cannot do better than this minima, right? That's simply the definition. Okay, so let's expand this thing a little bit to see what this actually is. And we're just going to expand it using fh minus f squared plus delta g squared plus 2 times delta g times times fh minus f. This whole thing times dx, right? Okay, I'm going to say that this can only be true. So first of all, this and this are the same thing. So it basically means this thing has to be greater than 0 for any delta g. And in particular, if I choose delta g to be very, very small, then this term is going to be small compared to this term, because of course the square of a very small number can be made to be much smaller than just the delta g term, right? Okay. If I choose delta g to be very small, that means this inequality can only be satisfied, can only be true if this integral only of the first order term, delta g fh minus f dx, is exactly equal to 0 for any delta g. If this is not exactly equal to 0 for some delta g, then I can always make this negative by taking the negative sign of delta g, right? And I can scale this delta g, for which this is negative, by a very small number so that the square term is insignificant. By doing that, I violate this inequality which I have to satisfy for fh to be a minimizer. Alright, so this is a proof by counter-argument that this equality has to be true for this inequality to be satisfied for any delta g. This is another interpretation of the concept projection. And by the way, this delta g has to be also in the space of xh, because fh is in xh, and this inequality has to be satisfied for any fh plus delta g also within xh, right? This thing has to be in xh. And fh is already in xh, which means delta g has to be in xh. So for any delta g within xh. This equality is another interpretation of projection. Again, let's use the example of this pen projected onto this blackboard. What this is saying is that if I take a delta g within that restricted space, which means I take a vector along this blackboard, that is delta g, okay? And this integration is basically an inner product. It means the inner product of any directional vector within the blackboard with the vector that points from the fh to this f, the inner product has to be 0. What's the other word for inner product being 0? Orthogonal, perpendicular, right? It means if you draw a line that connects the projection with the real object, that line has to be orthogonal or perpendicular to any tangent direction of this blackboard. Alright? Or the difference between FH and F has to be perpendicular to the whole space. And that is what this says. So that's a different interpretation of projection that is going to be useful